Hello class, welcome to our video on section 8.3, improper integrals, day 1 of the lesson. So our first introduction into integration of integrals that we call improper. So hopefully we end the lesson, you'll understand why they're called that. So we're going to start with a warm-up of problems we already know how to do. So we're going to start with the integral from 1 to 10 of 1 over x squared. So you should remember that if I were to do this problem, probably the best way would be to rewrite it as x to the negative 2. When I integrate x to the negative 2, I get negative x to the negative 1, or negative 1 over x, and I am going to evaluate that from 1 to 10. So when I do that, I end up with two values, negative 1 over 10 plus 1, and this gives me a value of 9/10. So part A has an answer of 9/10. All right, part B, very similar problem. The only thing that has changed is that the top bound is 100 instead of 10. So if I change this to be 100, then my first fraction becomes 100, and my answer is now 99 over 100. So similar answer to a similar problem. Okay, so hopefully you can see where this is going. Example C is the same problem, but with 1,000 as its bound. So I'm going to take my problem again. I'm going to change the top bound to be 1,000, which the integral is the same. I'm just getting a different numeric answer for the first part. So negative 1 over 1,000 gives me a new answer of 999 over 1,000. So now you can see that part D is a little bit different because the bound at the top is actually infinity. So we don't have two numeric values anymore, but a value of infinity as the top bound. So while I'm evaluating the integral the same way, I have this bound of infinity at the top here, which would realistically, or how you might think of writing it, you would put infinity in the denominator here. But we all know that you can't really evaluate something with infinity in it. However, you can do something that we have done in previous math classes, which is to think of that value of 1 over infinity representing the value of 0, because as infinity gets larger, you get larger and larger values in the denominator, the whole entire fraction approaches 0, which means the whole entire value is of 1. So hopefully, as I was saying that, you were thinking of a certain vocabulary word that we have learned in previous math classes, and that word is limit, which we will be using to evaluate these improper integrals. So here's our first definition that you'll fill in on your form. So we are looking at improper integrals that have infinite integration. So what that means is if you have a bound that is infinity at the top, or a bound of negative infinity at the bottom, then you rewrite each of the integrals as a limit. So you replace the infinity with a letter, usually we use A or B, that we will then be approaching infinity or negative infinity when we evaluate that integral at that letter. So in this particular situation, the top bound is the problem bound of infinity. So we're replacing the top bound with a variable. I'm going to call it b here, and then we're going to take the limit of this thing after I evaluate it as b goes to infinity. And then the same thing occurs down here in part 2. Part 3, just a little bit different. You have to break it into 2 pieces because you have 2 separate problems, or 2 separate issues in the problem. So the bottom bound is negative infinity, the top bound is positive infinity. So you need to break it into 2 things. The letter that you are filling in here is actually going to be a number. If I can, I try and use 0 in this spot. So pick a spot in the middle, wherever it works for you. 0 works great. And then you're going to rewrite the whole entire problem where you're approaching negative infinity. So this bottom bound is being replaced with the letter A, and this top bound is being replaced with the letter B, and the C's are actually going to be an actual number. So let's see how this works here. So, well, let's just read this real quick. So it says if the limit is finite, the improper integral converges, and the limit is the value of the improper integral. So it's a vocabulary word, converges. If the limit does not exist, then we say that the improper integral diverges. So your homework is going to ask you to say, does it converge or diverge? If it converges, find the value of, or what the integral converges to, is what we'll say sometimes. Okay, so here's our first two examples. They should be on your paper. So the first one has this upper bound that is problematic. It's the infinity upper bound. So we need to rewrite it with a value in place of infinity. So here's what it looks like. So I've replaced the top infinity with the letter A, and then put the limit as A goes to infinity out front. So all of this sometimes seems a little bit like not necessary, but it's definitely something that AP would expect you to be able to show. So make sure that you are writing this down so you can start to make sense of it. Okay, so from here now we can integrate this like a normal problem. So you might not recognize this for what it is. This is actually an inverse tangent problem, and I'm not going to go through the whole procedure with you. I think maybe that would be something good for you to do on your own. But in class tomorrow, you will have access to how to actually do that. So we can look at that tomorrow in class. So now you're evaluating this as from 1 to A are the bounds. So you're substituting top bound of A in and bottom bound of 1 in, and you're approaching infinity for the A portion of the problem. So the, couple things you need to understand, and you might want to graph inverse tangent as you're doing this so you can see it. So inverse tangent of radical 1, or inverse tangent of 1. So where does tangent have a value of 1? Well, that's at pi over 4. And this is what's happening as you approach infinity. Well, there's actually an asymptote and your inverse tangent function that as you go off towards positive infinity, it actually approaches pi over 2. So this part here, this inside the parentheses, is pi over 2 minus pi over 4, which is pi over 2. Pi over 4 times 2 is pi over 2. So maybe a kind of a leap in here that you might need to take a look at, but we are applying the limit at the end. Okay, so we're going to look at the next problem, and the next one actually has two infinities. One is negative, one that's positive, so we're going to have to break this up into an addition problem. So my first step, I didn't even put limits in it. I just rewrote it, separated it so it had some value in the middle. And notice I picked 0 again because that's, if I can, I want to pick 0 because that's an easy number to work with. So this is all I did in the first problem, first step, as I just rewrote it. Okay, so now I'm going to rewrite it again involving limits. So this part on the right-hand side is what we're looking at here. So I'm just dealing with this stuff here is now been rewritten as the limit as A goes to negative infinity from A to 0 of that function, plus limit as B goes to infinity from 0 to B of the same function. Okay, so hopefully, again, you recognize this for what this is. This one's actually easier, I think, for you to recognize. So that is also inverse tangent. Inverse tangent tends to appear quite a bit on these types of problems. So we're evaluating inverse tangent from A to 0, and then evaluating inverse tangent from 0 to B, and two different limits that we're approaching. Negative infinity for the first part and positive infinity for the second part. So here's what we get now. So we're substituting 0 and A in, and we're going to evaluate the limits. So as A goes to negative infinity, this actually has a asymptote at negative pi over 2. And this portion here, as you approach positive infinity, as I said before, is positive pi over 2. So I actually have a negative times a negative, so pi over 2 plus pi over 2 equals pi. Might be a good time if you need to pause the video and take some more notes on it, so that way you can get it all written down if necessary. Okay, next example. or next definition, actually. So this is if you have something happening in the middle of the two bounds, like a vertical asymptote. So if you have something that doesn't work in the denominator, so an undefined value in the denominator, then you have to rewrite the problem, again substituting a value in that you're approaching. Okay, sometimes the way this is written looks a little funky, so hopefully as I do the first example, what's written here will make sense. Okay, so I have maybe too much on the screen here for you, but this is the next example. I've uncovered the whole thing for you, so that way you can at least look at it as I'm talking, because I don't want to run out of time on my 15-minute video. So this one has a vertical asymptote at x equals 1. So I have to break that into two pieces, from 0 to 1 and from 1 to 2, because 1 is where the problem is at. So that's what's happening here in this first step here. Then I write it with its limits, and I'm going to write the limits as I approach it from the left and from the right. Again, I need to look at what's happening in the problem. So I've rewritten it in this for A to approach it from the left and for B to approach it from the right. The antiderivative of this then is negative natural log of the absolute value of 1 minus x. If you don't remember that, you might want to stop and think about it. And then we're going to substitute our bounds in and evaluate. Well, these two pieces here that I have in red, natural log of 1, and this is also the natural log of 1 when I'm done, are both 0. So those are not a problem. But this part here is actually a problem, and that's what this graph is over here. It's the graph of the natural log of 1 minus x. As you approach in 1 from the left or 1 from the right, you actually are going to negative infinity. So that limit doesn't exist. So since that limit doesn't exist, we say that the integral does not converge, and therefore it is a divergent integral. Okay, so we don't have an answer for this problem. Happens probably more than you'd think. All right, next example I've also uncovered for you so you can look at it all. I'm actually not going to do too much of this example with you. I want to get to the next one. So again, you might want to pause the video and look at my work, but this one does converge, and it converges to 3 plus 3 times the cubed root of 2, where the problem value is again at x equals 1, so it's been broken into two pieces. Again, pause if you need to, but I'm going to change slides. Okay, last one. Oops, sorry about that. The last problem we're going to look at is this same original problem that we started off with, but now it has two problems. It has a vertical asymptote at x equals 0, and it has a bound of infinity at the top. So we have to break this into two parts. So you're going to do the limit as you approach 0 from the right, and then you're going to do the limit as you approach infinity at the top. So that's what you have here in this first step. I've just rewritten it to look like that. Well, now I also decided to do what I'm calling fancy substitution, because this problem is kind of difficult to do. Which, remember how I told you before I was going to show you how to do it tomorrow? I forgot when I said that I had it on this slide. So even better, you can look at it now and you can go back to apply it to that original problem. So this, what I did is I let the square root of x equal u. So this is now going to be u, and then I squared x, and or squared the square root of x, and when I kind of left it here, but then decided to make it look like something that I also have in the problem. So I added 1 to both sides. So u squared plus 1 is this piece, and then took the derivative from here so I don't have weird square roots with negatives and whatnot going on. So I can now rewrite each of the integrals as 2u du over u times u squared plus 1. And then what's really nice with this is the u's will cancel here and here. So now you just have 2 du over u squared plus 1. Well, u squared plus 1 is, its integral is inverse tangent, and then I have the 2 out front. And you'll notice I also changed my bounds to be in terms of u, but it turns out they're the same bounds, so it doesn't even matter for this particular problem. Okay, so now I'm doing some substitution. So I'm substituting 1 in for u, a in for u, b in for u, 1 in for u again, okay? And so inverse tangent of 1, we already know is pi over 4. Inverse tangent of 0 is what we're looking at, is actually 0. Inverse tangent as you approach infinity, pi over 2. Inverse tangent of 1, pi over 4. Combine all the terms, and voila, you end up with pi.